So in this video I will do a past final because few of you asked me to record a complete solution to a past final. So I just randomly chose May 2018, okay, but I would like to stress the fact that this final was chosen randomly. So there is no reason why I decided to solve this final. And what I'm trying to say with that is that don't take this final as some kind of hint that your final is going to be similar to this one, okay? How you should proceed is you should try to solve this final by yourself first, and if you get stuck somewhere, look at the solution, and if that doesn't give you enough hint, then come and look at the solution, look at this video. I will not write the questions here, but I will post a link to this final, although by now I really hope you know how to find this final. If not, I will post a link of the final in the description. Okay, so we start with the first question. The first question is consisted of two parts. Okay, the first one is a homogeneous system. Okay, x plus y minus z is equal to 0, x minus y plus 2z is equal to 0, and 3x plus y is equal to 0. The question is find the general solution of this system. So it's a homogeneous system. Let's create that matrix. The coefficient matrix is 1, 1, 3, 1, negative 1, 1, negative 1, 2, 0 by the columns, okay? And because this augmented column consisted of zeros is not going to change, I'm not going to write it. So here this is a straightforward reduction of this matrix. Row reduction, row 2 minus row 1 is my new row 2, and row 3 minus 3 times row 1 is my new row 3. 1, 1, negative 1, 1 minus 1, 0, negative 1 minus 1, negative 2, 1 minus minus 1, 3, 3 minus 3, 0, 1, minus 3, negative 2, 0, minus 1 times negative 3, that's 3. Okay, so I have the two identical rows here, or even if one of them was a constant multiple of the other, that would just become the 0 row. So what happened here is row 3 minus row 2 is my new row 3. Okay, so I have the pivots in the right place. Now I'm gonna make this one a leading one, so that's negative 1/2 times row 2 is my row 2, and I get 1, 1, negative 1, 0, 1, negative 3 over 2, 0, 0, 0. And now the backward phase is when I eliminate the element above the leading one. So the last step is row 1 minus row 2 is my new row 1, giving me 1, 0. So negative 1 minus minus 3 over 2, that's negative 1 plus 3 over 2, and that's 1/2. 1/2, 0, 1, negative 3 over 2, 0, 0, 0. And here, if you want, because there is no row reduction anymore, you can put this column. You don't have to. So this stands for x, y, and z. Okay, so z doesn't have a pivot, so that's the free variable. Y is equal to 3 over 2t, and x is equal to negative 1/2 t. From here, the solution is the vector x, y, z. So that's negative 1/2 t, 3 over 2t, and t. I factor out t. Somebody wants to maybe factor out 2t. That's up to you. And you're left with negative 1 over 2, 3 over 2, and 1. So this is the parametric form of the solution. Okay, now the second part of the question, B, so this was A, and now B, it says find the general solution of the system x plus y minus z is equal to A, x minus y plus 2z is equal to B, and 3x plus y is equal to C. Okay? Okay, so this is not a homogeneous system, but it says that a particular solution is given to this system such that x is equal to 1, y is equal to 1, and z is equal to 1. To this system. Okay, so I already know one particular solution. This solution here is a particular solution, and the question says find the general solution of the new system. So here, similarly to the question on the first test that we did sometimes in September, I'm not asking you to put this in a augmented matrix and start row reducing. Basically, this question, I would be surprised if it's more than 1 point, asks you whether you know how the general solution is obtained. That is basically the particular solution, one particular solution, plus the solution of the homogeneous system. Okay, so the answer is the particular solution plus the solution of the homogeneous system. That's it. Okay, so please be careful about that that point right here. Okay, now the second question says show that I will write here the question because we have to prove this, so it's always good to refer to what I'm using. Show that for any square matrix all the vectors in null of A must also be the null space of A n. Okay, this A n means A times A times A times A n times, right? And then it says that where A is greater than 1, right? Because if n is equal to 1, then I get my hypothesis. Okay, there's nothing to prove. Okay, so what is given? It's given that u, or let's say the vector I wrote, v, is in the null space of A. What does that mean? If a vector is in the null space of V, that means that this matrix equation A times V is equal to 0. That's what means for a vector to be in the null space of A. We want to show that V is also in the null space of A to the power of n. So we want to show this. In other words, what does this mean? What does it mean for V to be in the null space of an? It means that, in other words, we want to show a to the power of n times v. When would v be in the null space of an? If an times v is equal to the 0 vector. Well, let's show this. Let's show that this is satisfied. an times v is the same as an minus 1 times a times v. When I was explaining this to some students in the class, I realized that you guys get confused. What does this mean? This is like a to the power of 3. It's a, 1 factor of a, times what? Times a to the power of 2, right? So that's 1 exponent less times 1 factor of a. Similarly, a to the power of 100 would be a to the power of 1 factor less times a. Now, if you multiply this, you would get a to the power of 100. Then for any general n, I get a to the power of n minus 1 times a times v. But this is nothing else, a to the power of negative 1 times how much? Times the 0 vector. From where? From the hypothesis, from the assumption, and that's simply equal to the 0 vector. So from here it follows So what we have shown that a to the power of n times v is the zero vector, which means that v is in the null space of a. Of course, this part of the proof here was just the explanation for you. From writing out the assumption, right, spelling out what does that mean, you can jump into this line and you're done. Okay, problem number 3, we have some interpolation of a polynomial. The condition is given that you have to find this quadratic polynomial a0 plus a1x plus a2x squared, okay, which means figure out what is a0, a1, and a2, such that what is given? Such that the graph of this passes through some points here, this one, and this one. And these points are given to you, okay? So the points are -1 and 6, 1 and 24, and 2 and 48. Well, don't forget that these stand for x and y, right? So that means p evaluated at -1 is equal to 6. That's what it means. Here means p evaluated at 1 is equal to 24, and p evaluated at 2 is equal to 48. Well, let's evaluate this polynomial at -1, 1, and 1. So that's a0 minus a1 plus a2, right? If I plug here -1 for x, if I plug here -1 for x, that -1 squared is positive. Then p of 1, it's a0. I plug 1 here, so you get plus a1. I get 1 here, 1 squared is plus a2. And evaluated at 2, it's a0 plus 2a1 plus 4a2, because 2 squared is 4. But then I just have a linear system: 1, -1, 1, 6, 1, 1, 1, 24, and 1, 2, 4, 48. And then you start just row reducing. Row 2 minus row 1 is my new row 2, and row 3 minus row 1 is my new row 3. So 1, -1, 1, 6, 1 minus 1, 0, 1 plus 1, 2, 1 minus 1, 0, 24 minus 6 is 18, 1 minus 1, 0, 2 minus -1, 3, 4 minus 1, 3, 48 minus 6 is 42. Okay, here I will simplify this. 1/2 times R2 is my R2, and 1/3 times R3 is my R3, which gives me 1, -1, 1, 6, 0, 1, 0, 9, and 0, 1, 1. What do we have here? 42 divided by 3 is 14. Okay, so I have the two leading ones where I need them. Now I will eliminate this one but need the leading one. So 1, -1, 1, 6, 0, 1, 0, 9, 0, 0, 1. 14 minus 9 is 5. As you can see from here, I already know what my A, this stands for A0, A1, and A2, right? A0, A1, and A2. So from here I know that A2 is equal to 5, and from here A1 is equal to 9. Well, if you have these two values, you can plug them in any of these equations, and you can find what is A0, or simply continue row reducing this. R1 minus R3 is my new R1. So that's 1, -1, 0, 6 minus 5 is 1, 0, 1, 0, 9, 0, 0, 1, 5, and finally row 1 plus row 2 is row 1. So 1, 0, 0, 10, 0, 1, 0, 9, 0, 0, 1, 5, and obviously we got what A naught is. A naught is 10. Finally, P of x that satisfies this condition, the quadratic function passing through these 3 points, is A naught, so that's 10 plus 9x plus 5x squared. Okay, so problem number 4. Problem number 4 is straightforward. You're asked to find, actually they give too many hints here. It says consider A and R, it's reduced to row echelon form. Using the columns of A, give two distinct bases for column A, and they, as I said, they give this extra hint that you have to refer to the columns of A, not to the columns of R. This hint usually is not there. You should know it by yourself, that you have to look for the dependence relation in the reduced row echelon form, but to remember that the column of A is constructed by the columns in the matrix A, not its reduced row echelon form. So as you can see from R, I have 3 pivots. That means that I will have three vectors in the basis. So the dimension, the rank of A is 3, which means the dimension of the column space of A is 3. So I need the 3 vectors. The one obvious choice is to take the columns from A that correspond to the pivot columns in R. So problem 4, one basis would be consisted of the vectors 4, 3, negative 2, 5. Then the second column 5, 1, negative 1, 2. And then I have a pivot in the last column, in the fourth column, and that's 3, 5, 2, negative 1. 3, 5, my bad, 2, negative 1. But I can find another 3 independent vectors. For example, the second column, the third column, and the fifth column are also independent. Or the second column, the third column, and the fourth column, and so forth and so forth. So another solution would be 5, 1, negative 1, 2, negative 12, 2, 0, 2, and 8, 17, negative 5, 18. That's it. There are other different answers, right? Problem number 5, I have to solve for the matrix A. That means isolate for A. Okay, so here you have to be careful. I cannot find the inverse of a sum or a difference. Don't mix this with the sum or a difference of a transpose of a sum or a difference, right? This one here, I cannot drop the parentheses. So in order to isolate this, in order to drop the parentheses here, what do I need to do is I need to take inverse on both sides. So the inverse of this would be equal to the inverse of this. Okay, an inverse of an inverse is just C minus 2A, but here you have to be careful, okay? The inverse of the product is the product of the inverses with reversed order. Okay, so I have B inverse, A inverse is just A, is equal to C minus 2A. Now bring all the expressions involving A on one side of the equation. So that's B inverse A plus 2A is equal to C. And now factor A. But of course you have to be careful. I can factor it only on the right hand side. So this is A, B inverse plus 2. So be careful not to get caught in this problem here, because if you factor A here, right, you're not going to end up with a constant 2, but a constant times the identity matrix. And finally, I need to isolate for A. Well, I will multiply this matrix by its inverse in order to get I, right? And then A times I is finally just A. But if I multiply this side on the right by B inverse plus 2I inverse, right, in order to get an A, I have to do the same thing with the right hand side. So C times B inverse plus 2I inverse. So this is I, right? I times A is just A. B inverse plus 2I inverse times C. Okay? And now it says using the fact that if, so in part B, if the matrix B is 4, 1, negative 3, 1, negative 1, sorry, and C is 2, 3, 5, negative 3, says evaluate how much is A for this particular B and C. Okay, well, what do I have to do? First I have to find B inverse. Okay, so from here B inverse is equal to 1 over the determinant. The determinant of 2 by 2 matrix is 4 times negative 1, it's negative 4, minus 3 times negative 1 is negative 3, times, be careful how these entries here will flip. The entries on the main diagonal, they change their positions, negative 4 and 1, and the entries on the other diagonal, they just get multiplied by negative 1. This whole thing is negative 1, so B inverse is 1, 1, negative 3, negative 4. Okay, so then from here, A is equal to B inverse is 1, 1, negative 3, negative 4, plus 2 times I is 2, 0, 0, 2, the whole thing inverse times the matrix C, which we are going to introduce very soon. Okay, so let's add this 2 plus 1, 3, 1 plus 1, sorry, 1 plus 2, 3, 1 plus 0, 1, negative 3 plus 0, negative 3, and negative 4 plus 2, negative 2. And this is inverse times C. So again, this is going to be 1 over the determinant, 1 over 3 times negative 2, negative 6, minus negative 3 times 1 is negative 3, times the matrix negative 1, 3, negative 2, 3, times the matrix 2, 3, 5, negative 3. And this is equal to negative 1/3, that's negative 1/3, times negative 2 times 2, negative 4, minus 5 is negative 9, negative 2 times 3 is negative 6, plus 3 is negative 3, 3 times 2 is 6, plus 15, 21, and finally 3 times 3 is 9, minus 9 is 0. Multiply everything by negative 1/3 and you get 3, 1, negative 7, 0. Okay, so here we have problem 6, again something to prove, so I'm going to write this down. Let the vectors u and v be in Rn such that if the vector u plus v so this whole vector is orthogonal to v minus u minus v, then u and v must have same magnitude. Okay, so here basically what you have to do, you have to use the properties of the dot product. So what are those properties? First, we know that if u is orthogonal to v, this implies that u dot product of v is equal to 0. So if the dot product of two orthogonal vectors is 0, which implies that for our case we have u plus v dot product u minus v is equal to 0, and this is going to be our starting point. But also what we're going to use later on is that the norm of any vector squared is just the dot product of that vector by itself. Okay? So let's see. U times u is u dot product u. Be careful here, I just want to remind you, and this is very important, there are only two products between vectors, the dot product and the cross product. So if you see a dot in between two vectors, that means it's the dot product. If you see an x between two vectors, that means it's the cross product. So I've seen a lot of, first of all, confusion between the two products and sometimes complete nonsenses. So you have to learn the dot product and the cross product, how to identify them. If you see a dot between two vectors, that means the dot product. The cross product is if you see an x between them. Minus u dot product v plus v dot product u minus v dot product v is equal to 0. So basically I have here distributed these expressions across the parentheses, right? Using this property, this simply becomes the magnitude of the u squared minus u dot product v plus the dot product is commutative, so that's u dot product v minus the norm of v squared. But these two will cancel, okay? And I get that the norm of u squared minus the norm of v squared is equal to 0. Well, you can, these are just numbers. This is the norm, right? These are norms. So those are numbers. So this is u squared is equal to norm of v squared. As a matter of fact, these are positive numbers. So from here it implies that the norm of u must be equal to the norm of v. And we have exactly obtained what was asked. The norm of u is equal to the norm